Okay. I want to warn you that this is going to be a big deal. There's a lot of notes in this lecture. It's a very long lecture. Hopefully we can check in along the way. And I just need you to please write your questions on the side. For something like this, where I know that there are a bunch of study goals that all require notes, one after the other, it can get kind of clunky to interrupt everybody's viewing. So I just make this a really big video, and then I assume that you can keep track of your questions. Something that's really important. On the side of your notes, please write the number of our school day or the date so that you can go back to Neo and find the corresponding lecture. When you're looking at your notes, if you've got a question, it's helpful if you know when you saw that video. So pause for a minute, make sure that you have the appropriate date and or the day number so that you can come back to watch this video again. All right. There was perhaps a bit of confusion, my fault, between a turbine versus a generator. The turbine is a way to spin a generator. It's a way to use mechanical energy to power the generator. And that generator creates current when a magnetic field passes over a wire. However you give that power, you're spinning the turbine. The turbine is the part that you interact with to move the magnets inside the generator over many, many wires, and at every pass that adds current. So you could power a turbine by blowing on it. You could power a turbine by letting a waterfall spin that turbine. And technically, the turbine is the thing that spins the shaft of the electric generator. So we're going to use a bunch of different ways to generate electricity today. And so I just wanted to clear that up. It's a very small point. You already had the concept about the magnet and the wire. I just want to name the parts a little more carefully. Remember that you can spin that turbine directly, or you can spin it with pressurized steam. That's how geothermal, solar thermal, ocean thermal work. That's how coal burning power plants do it. They burn coal to make a fire that boils water that puts pressurized steam to spin that turbine. That's how you use natural gas. That's how you use nuclear. Nuclear is just a way to boil water. And when we're talking about steam, it makes sense as a way to translate energy inputs to electricity, because water's very cheap and it boils at a pretty low temperature. So it's a great way to turn heat into spinning a turbine. I just don't want you to think about a hot tub, like the way that steam is fizzling. I want you to think of like a tea kettle where the steam is shooting out super hard, so hard that it can make a whistle sound. The concept you're going to need, it's worth putting in your notes, is that when we talk about steam, it's not like casually rising off the jacuzzi. It's being shot at very high pressure through a really small escape. So keep in mind, you're moving an extremely large, extremely heavy turbine that's connected to a generator that weighs in the tons. So it's not like fizzling steam. That would not move such a thing. You need to generate tremendous forces. So the steam is under really high pressure. When we talk about steam, remember that that'll be high pressure, okay? Now here we go. I'm going to go out of order, a whole bunch of study goals. Number 33 is about the wind. And this is probably the simplest way to spin a turbine. You just hold it up in the air and you engineer that turbine to cover a huge area. The more area you cover, the more wind you can capture. Wind blows, turbine spins, and the generator makes electricity. That's really all there is. By the way, technically there's a gearbox So whether it's spinning slow or spinning fast, the generator is always going at the same speed. The same way that you have gears in a manual transmission car. Some important trends for you to note. Wind is increasingly becoming cheaper. It's competitive with fossil fuels today, and that's a really big deal. At the global level, you can just about these days pretty darn nearly build a wind power plant for the same price that you could build a natural gas or a coal power plant. The price has become much more competitive. These tend to use a lot of land, and that's a concern. You can fit a nuclear power plant inside the high school auditorium, but a wind field is actually like kind of a lot of land, and you have to be picky. There's like, if you look across the landscape, you take the ridges of mountains or a place on the other side of a mountain pass where wind is focused. And so, you know, you really can't put them anywhere. That's a limitation. They're also really devastating for wildlife. They do kill birds. Birds look down, they don't look up. So they get hit by the thing on the way down. And they kill bats. Bats are really agile. They know it's there. They don't get hit by it. But when they go around flying around a turbine, there's a difference in pressure. You go from like a high pressure environment in the front to low pressure in the back. Maybe you know how the wing of an airplane works with like high pressure creates lift. So anyway, the same thing happens with a wind turbine. And when they fly around it from high to low pressure, their lungs get pulled out of their bodies. It's horrific. These really do kill birds and bats. You could probably fix this. You just have to scare away the birds and the bats. But it is a significant conflict among environmental groups. The Audubon Society is a little bit more nervous about wind power unless you have excluder devices to scare away birds and bats. They're like fancy kazoos, and they just go and they like make a sound. Okay. These are really exciting to other environmentalists because there's no emissions, extremely little maintenance, and it's basically forever. I mean, they're like totally renewable because we're never going to run out of wind. And we can keep going for a very long time. Once you build a wind turbine, it has an extremely long future. And, you know, maybe you got to replace a few parts that wear out like a car, but they're modular enough that it's really doable. You should know, though, that we built fields of turbines in the past that were very small. And it turns out that that's not very smart. When you drive through Palm Springs, like heading down to like the deep south of California, you come down that hill after the big dinosaur statues that were in the Pee Wee Herman movie. You come down the hill and all of a sudden you see this field of turbines. There's like 50,000 small turbines. Most of those aren't working anymore because it's not worth the maintenance. Then there will be a couple hundred medium turbines. And most of those are working because they might as well. But then there's like 10 or 15 large turbines and like 1 or 2 double extra large turbines. And those 1 or 2 extra large can do all the work of like 10 or 15 large, which can do all the work of like 150 medium, which can do the work of like 10,000 small. You see, there's this really easy math. When you make a radius a little bit bigger, you've quadrupled. Sorry, when you double a radius, you've quadrupled the area. And if you quadruple the area, you can catch way more wind. We say about 10 times the power. So the future is in making bigger turbines. Also, because of land use concerns, there's a really hot future for putting these in the ocean. Wherever you have a shallow coastal shelf, you just put them offshore. And by shallow, I mean 200-300 feet. So pretty much from Santa Barbara to where the oil rigs are, all of that would be useful for wind turbines. And in the crazy distant future, there's conversation of putting wind turbines up in the jet stream. That's nutty. It's 30,000 feet in the air. The idea would be that it's like a boomerang with a bunch of turbines on it that you have to figure out how to get up there, anchored to the ground like a giant kite, maybe. But a couple of those could power the entire United States, because up there the wind never stops. It blows extremely fast, and you'd have to like protect that airspace with military intervention. So this is like some really complicated, sketchy science fiction, crazy distant future. But people are on it. That would solve America's electricity needs forever if we could just get like 2 or 3 of those up in the air. So you could replace like $1 billion industry with 1 or 2 projects. And so people are funding that. Remember that it's pretty simple. You can see these homies sitting on top. I guess it's one guy. And like it's just a turbine connected to a gearbox connected to the generator. That's all there is to it. You can see the turbine on the ground. Sooner or later, they'll use a big old winch to pop those blades on there, and then they walk away. Remember that small ones are kind of going out of fashion. We're going for larger. And we're also considering ocean fields. That might be easier. That's more available. Like if you're trying to add something in a big crowded area like Los Angeles or Santa Barbara, that may be hard to find. But ocean real estate is more viable. In the US, we're really finicky about this. There's like a really loud opposition that says they don't want to look at this and that's going to hurt their real estate prices. But in many parts of the world, those concerns aren't as loud. And many parts of the world, ocean is happening. You can see bigger, bigger, bigger. Some of the largest ones in the world are built here in Goleta, where I'm lecturing you from. And if we can just make them a little bit bigger, they give so much more return that it kind of justifies the price of getting into giant wind turbines. 2 of these can replace a nuclear power plant. And so like that kind of makes sense looking at the cost of a nuclear power plant. Remember I told you the jet stream is really, really fast. So we're trying to figure out if there's a way to get turbines up there. Someday, if you're bored, we can talk about this. I don't think the College Board will ask, so I'll move on. Number 31, skipping backward a couple, is hydroelectric, which are regular old dams. And this is also simple. As a river is flowing down a canyon, you block it with a dam so that the water builds a huge pool. We call that a reservoir. You can use that water for other things. So this is a dual use concept. You get electricity. We'll talk about that in this unit. And then you get water. We'll talk about that in the next unit. Then when you let the water out, it's rushing out at high pressure. So that'll spin a turbine, generator electricity. And this is also pretty easy. In terms of electricity, it's beautiful because you can have it when you want. You see, the wind blows when the wind wants to blow. But with a reservoir, you can make electricity when you want it. You let the water out. If you need more electricity at 8 in the morning, you let more water out at 8 in the morning. And then if you don't have a need for electricity, you can just shut off the water and you can store that potential. The fact that you can store it is huge. Among the renewables, that's a really big problem. It's sunny when the baby Jesus says so. It blows wind when the baby Jesus said so. There might or might not be swell in the ocean at a particular time. But if you can control this water, that is a big whoop. Unfortunately, we built all of these at a time when labor and material and energy were really, really cheap. But as our economy continues to modernize, labor's become expensive, materials become expensive, energy's expensive, and we have a bunch of environmental regulations now. So building a dam in the United States is just impossible. We haven't built a dam in the US since the 1970s, a big dam. And globally, there's like a sweet spot in a country's economic development when you can afford it and it helps. But they really, like, the cost just isn't really reasonable for many modern economies. Plus, rivers carry sediment, and when you slow down the water, that sediment will settle, right? Like, you understand that concept that when there's no surf, the water's really clear. So reservoirs don't last forever. And so a lot of people are starting to look at these investments and say, well, even if I could build you the dam, in 70 years, that's going to be full of sand, or in 150 years, that's going to be full of sand. And then there's this tremendous cost of trying to get rid of a thing like this, which has basically never been done for big dams. And so it's looking like a really sketchy investment. These are declining because of cost and longevity. By the way, all these bullets are notable. Nowadays we care a lot more about ecology in rivers, and blocking the flow of water is ecologically really important. We'll talk about that in the next unit. So in a country that starts to protect its ecosystems, you also would never build big dams. No emissions, very little maintenance. So we say that this is renewable, like rain keeps coming, but maybe not sustainable because there's other hidden costs, like the long-term investment money and the river impacts. I think I've said everything else. The future for dams is teeny ones, very small dams, mini dams that can be cheaper, they can be local, and they don't have big ecological impacts because you're just diverting a little bit of water instead of blocking a river. I'll show you an example in a minute. The basic idea of a dam is this. So you block the water, making a reservoir, let the water out. That powers a turbine, which powers a generator, which puts electricity out on the line. And so when you let out the water, it comes out pretty hard. That's actually a lot of power. Look at the size of these generators. That's Hoover Dam. Those are some really big generators. These are some of the largest electricity facilities on the planet. The largest producer of electricity on Earth is a much larger dam that was recently completed in China called the Three Gorges Dam. And that's a pretty frightening project that's probably doomed to fail, but we'll talk about that another time, I guess. Look at this idea. What if you just diverted a little bit of water, kept it in a pool, and then when you need just a little bit of electricity, you let that water out and it runs a smaller generator. Miniature or small scale dams do seem to make sense if you consider the lifetime cost of providing electricity to a house or a neighborhood. The one-time investment of building one of these, because you can also route a little water for other purposes like irrigation, this actually does have some potential economically. Mini dams, micro power dams. Okay, skipping again, number 35. We're going to start doing thermal stuff. So that means we're going to be making steam now. And for geothermal, you've got free energy if you've got heat under the ground somewhere, like lava near the surface of a tectonic plate. If there's a thin tectonic plate where there's like magma underneath it, I guess it's magma, not lava, right? Lava's on the surface, magma is not. So that should say magma, not lava, sorry. You just drill a hole, pour water down, and where that water migrates to something that's hot enough to boil it, it'll allow steam to come out somewhere else. You just put a turbine over the steam and voila. This is the same as like Yellowstone. So water is soaking in somewhere and then it's going poof, so it makes a vent of steam. And so the idea goes, why don't we just make fake geysers? And it's pretty darn exciting because if you've got the water, it's basically endless electricity and it's very reliable. You can turn it on, turn it off whenever you want, so you can be in control. That's really important. It's not like the magma is going to run out of heat, so you're basically in charge of the power. Um, Big downside is you can just put it where there's the right stuff. It just so happens that the United States has a pretty good amount of this. So in the US, we could keep expanding geothermal energy, and we have been for a while now. But you have to be like near a mountain or a plate boundary or a volcano where the magma is pretty close to the surface. The fact that they have zero emissions and very little maintenance make these super sustainable. The cost is still kind of sketchy. You know, if we had a carbon tax, then it would make the competition more expensive. But if you have the right crust, you're stoked. If you don't, nothing you can do. Fun fact, Iceland has unbelievable potential. Iceland is the only country that's dead centered over an expanding crust. So where there's, what do they call it? A divergent plate boundary. There's like a lot of magma very near the surface. And Iceland is like, oh, great. We're going to be Saudi Arabia of carbon-free electricity. They're almost carbon-free now. They've been using very little fossil fuel energy for many years. I'll show you in a minute. And they also have copper mines and electric mining equipment. So they're going to build this giant extension cord, and then they're going to power like England, Scotland, Ireland, and potentially all of Europe. It's not a joke. They're just going to sit back and collect payment for all of their basically unlimited geothermal power. The idea goes that you pour in water one place, it runs over to where the dirt is hot enough to make it steam, the crust is hot enough to make it steam, and then that steam is captured to power a turbine. Here's the same idea. You can reuse the water if you can capture the steam, so you can cool down the steam and then inject that same cooled stuff. This diagram might not make sense because it looks like the same cycle, but you can heat up a house on a small scale, and then you can take hot water from inside of a hot house, drive that down to a different part of the crust where it's cool. So you can run home heating in hot crust, and then you can run home cooling by passing hot water through cold dirt to bring in conditioned cold water. So this would be like radiant heat, radiant cold. George W. Bush has a ranch in Texas, which has been doing this for like 40 years. It's pretty straightforward if you find the right dirt. Speaking of the right dirt, you may know that Iceland is famous for these giant hot springs. And you may not know that it's the only country on a divergent plate boundary, so they've got a lot of thin crust over magma. And you know what else they have is a crap ton of mountains and glaciers and snow. So like the water is just running to the ocean anyway. So as Iceland has grown, they've been making less and less of their electricity with coal. Coal is completely done in Iceland now. They've been using less and less oil for energy. They basically just use that for home heating. They've increased their hydropower over time because, you know, a lot of rivers and they need to distribute water anyway, so they might as well make some electricity. But the geothermal thing is the big whoop. This is just until 2008. Now that it's 2020, the hydropower has stayed at that number. The oil has started to shrink again, and the geothermal has just blown up. And their forecasts for the future are to produce more than double their current total energy budget. They're going to more than double it just for the purpose of starting to sell it to other countries. Keep in mind, that's a pretty small country. The United States is still much bigger, so we make a teeny amount of US energy, but that's still the world's largest geothermal total. So remember that this, which is more than any other country, is still 0.2% of our US electricity budget. So this is still small potatoes, but the potential is massive. Number 32 is ocean or tidal power. There's a lot of ways to use the ocean because there's a lot of energy in the ocean. Look at how much water it is. Look at how much heat it holds. Look at how much it moves. As a general rule, you should probably try to understand which of these are all the time and which are just some of the time. And as a general rule, you should remember that these are delicate ecosystems and that salt is difficult on engineering. Like salt just messes things up. If you talk to anybody who's got an ocean boat, they'll tell you that salt is just evil. And that all the wildlife in the ocean, all the critical impacts of human activity in the ocean, this is a touchy subject. Wildlife impacts and corrosion issues. I need you to understand all four of these, so I want to explain them in order, okay? Number one is tidal barrage, and basically you bar a bay. So you take a bay and you make it into a reservoir by building a dam across it. You can see here on the screen, the barrage is the dam that closes off a bay. And then, because it's closed off, you can control when the water goes in and out. So watch my hands, please, in the speaker view. At high tide, you open the dam and water floods into the bay until you fill your reservoir, and then you shut the dam. Wait for low tide, and then you allow the water to exit, and that powers the generators until you've equaled low tide, and then you shut the dam. So for a few hours, you're not making electricity while ocean level goes up. And then when you're ready to go, you open the penstocks or whatever it's called. The bay fills up, making electricity, and there's like a rhythm. You get a burst of electricity when there's a big differential, then you don't get any electricity until the other one. This will probably not work out. It's got a really scheduled supply, and that's a big deal. I can tell you when high tide is tomorrow. I can tell you when high tide is on my birthday in the year 2049. Like we know when there will be high and low tide. So that's good that you can schedule it. And it's totally renewable in the sense that there's always going to be tides. But these are like some of the most delicate parts of the ocean ecologically because wildlife comes in to breed there. This is also important because a lot of nutrients flow out to the ocean there. And so they're really critical to wildlife. Anybody who fishes understands that bays in the ocean are extremely important to wildlife. Also kind of a bust because the strongest tides are in the north or the southern latitudes. Like there's no tide at the equator. So because the strongest tides are way to the north and south, that's nice, but people don't live there. There's not a lot of people there. Most people live closer to the middle of the planet, temperate and tropical zones. So where it's really a lot of potential and it pays off, there's no people. Where you've got all the people, those bays are just not producing a lot of tidal change. The maintenance stuff sounds like a nightmare too. Number two, there's a bunch of ways where spinning turbines can be powered by moving water. There's more names than I know, but one option is you just submerge a turbine so it's in the current. And the other option is you can turn the turbine sideways and build them up on a reef. So all the passing water is forced to go through what's called a turbine reef. That's like shallower water, like the outlet of a shallow bay. One reason that this kind of sucks is you saw those big generators, right, in the previous slides? That's got a lot of resistance. They're heavy and there's a lot of magnets pushing off a lot of wires, right? So the resistance is really strong, but if you make a big turbine under the water can just go around, right? Like water doesn't have a lot of focused energy in the ocean. So when you put an obstruction, you might be able to get a turbine to spin, but then that's also just deflecting water around it. So it's actually really difficult to like focus all that water energy to make that into power. These have pretty limited efficiency. They have limited potential. We're always talking about putting these where it's shallow, which tend to be really sensitive habitat. You can imagine if this thing was spinning fast enough, it's just a blender for wildlife. Sand and salt is an even worse combo. This might make sense where a big bay funnels out into the ocean, but so far there's been a lot of research and pretty limited results. This one also kind of skeptical. Next. And by the way, remember to write questions. If you have questions, I can answer them later. Next, ocean thermal. Here, we're going to make steam, but it's not water steam. Okay, bear with me. Please look at the smaller diagram. I'll explain what's happening down here. Okay, in places where the ocean is hot, like along the equator, you can take something which is not water, pass it over hot ocean water until that substance boils. You see, the secret is salt water boils at a pretty high temperature. So the ocean gets to 85 degrees all the time, and that will not boil. But something like ammonia does boil at 85 degrees. So you need what's called a working fluid, and that's the challenge to this engineering. In this cycle over here, you don't have water, you have a working fluid, and you should put this into your notes, of course. The working fluid is special because it will boil at 85 degrees. So you pass some hot water pipes, ammonia hits those pipes, and at 85 degrees, the ammonia makes steam. So you use an ammonia steam turbine, and then that ammonia is cooled back down using cold water from the bottom of the ocean. You understand that that's not ammonia and water mixing, right? That's in pipes. So cold water in the pipes will turn ammonia steam into liquid ammonia. Then the liquid ammonia will reach really hot pipes, and then that liquid ammonia will be boiled by the pipes. The water and ammonia don't mix. So the ammonia is in a closed loop. The ammonia is made into steam by hot pipes and condensed back to liquid by cold pipes. You get hot water from the surface of the ocean, you get cold water from the bottom of the ocean. Pow. The whole challenge here is how you're going to get, 10 million gallons of ammonia or whatever fluid they're using. Once you have it, it's easy because you use hot pipes to make the steam and the turbine and the generator, you understand. The real challenge is finding the working fluids that can boil at a low temperature. We have installed a few small ocean thermal facilities. They do exist. They're not exactly cranking power out, but they exist. Last is one that I actually think has huge potential. What if you can use surface action to move air? So the idea goes that where you've got surface action, if you make a container As the surface action goes up and down, the water underneath will go up and down. You can see it in the diagrams here. The white diagram is probably the easiest one. So as this water goes up and down, that column goes up and down. So you're pulling air in and out. See, when the water rises, that's pushing air out. And when the water falls, that's sucking air in. You can run a whole bunch of these independently, like each of them has their own turbine, but you can also put 3 turbines on a single shaft to run a generator, or you can push air up a whole bunch of water columns to power a generator. You can have valves that close off on 2 sides of a turbine. So the outgoing air spins the turbine this way. And then when you need to suck air in, this flap opens and the incoming air keeps the turbine spinning. So you can have exiting air and entering air on the same turbine. Push the air out and it spins. Suck the air in and it spins. This is nearly constant, because if you've got surface action, wind blows across water in very reliable patterns. There's places where the ocean is very windy. You have a lot of surface action, so it's almost constant, because when the piston's going up, you're powering, and when the piston's going down, you're also powering. You can do this on the shore using stuff at the beach. You can do this near shore, like on a pier, or you can do this offshore, like on a barge. And, you know, since you're not really messing with the ocean bottom and you're not really affecting the water, this could also be habitat for fish farming. Like you could hang bags of oysters off these. I think these seem pretty doable. They haven't been made large yet because ocean real estate is kind of hard to find. But I think that the nearshore and the offshore stuff makes a lot of sense. Oscillating water column. And I didn't include this one because it's still kind of in the engineering phases, but there's other ways to use surface water. In this case, you're moving cables up and down, which moves water to spin a turbine in another way. They're hydraulic rams. Anyway, I didn't include this one, but there are other ways to use ocean power. We're getting close to finishing. I know it's a long lecture. Remember to keep your notes on paper, your questions on paper. There's a lot of ways to use biomass. Biomass is current carbon. It's not fossil carbon. So you're taking carbon out of the atmosphere to grow the biomass, and then you're burning that biomass. So the carbon you get was just in the atmosphere a minute ago. That's not climate consequences. And you should probably know that in least developed countries, this is the #1 source of energy. In least developed countries, that's what LDCs are. 4 options. You can just burn stuff, like forestry stuff and agriculture stuff. You know, you just plain old fire. So you can heat homes, you can boil water, you can cook your food. This is the #1 energy source in least developed countries. Or you can use large volumes to make a bunch of steam to spin turbines. You can make electricity out of this. #2, you can do digestion of biomass. So you can take organic compounds that are already available, like manure from a feedlot, or wastewater from Santa Barbara, or you can go to your landfill at Tahigas. And wherever organic stuff decomposes without oxygen, anaerobic decomposition, you make methane. And so now that you have natural gas, you can just use that like other natural gas. You can make heat, you can power steam electricity plants, or, by the way, you can power a steam plant and then use that steam as a heat source. That's called cogeneration, and that's a vocab term that I had to sneak in somewhere, so there it is. It's underlined on the screen. Cogeneration. When you use methane to power an electric power plant, and then you use that leftover heat as a heat source to warm houses or to do industrial work or whatever. Option number 3, you can ferment sugar into alcohol. Now remember, if you're using agricultural sources, we call those energy crops, you're probably spending more carbon to grow it than you're saving by using the energy crops. So we say that agricultural sources are no good. But if you can find a waste source of sugar, like parts of the sugar cane that you don't eat, then it's just harvesting trash to make alcohol. That could work. Remember that ethanol is used to cut gasoline so that you're using less fossil fuel and more biofuel. There's a lot of oils that you can react to make biodiesel. We talked about vegetable oil already, and that's another type of biofuel. It's biodiesel. Ethanol is like bio for gasoline. Biodiesel is just the name of diesel that comes from plant oil. And there's some cool, creepy mystery stuff coming about algae. I don't know enough. There's too many options. But we might be able to use algae for cool stuff. Fuel cells are tough to explain. I'm sorry, this is a tricky one. I mean, I can explain it, but I just don't think you would need to. It's tough because we have limited time. The way that this works is there's a catalyst. Oh, crap, sorry. There's a catalyst on one side, and catalyst is a thing that makes a reaction happen. So when you give it fuel, like hydrogen fuel in a hydrogen fuel cell, there's also methane fuel in methane fuel cells. So when you give it fuel, I don't know how much to explain here. It basically creates polarity. You're like charging the battery when you feed it fuel because the catalyst separates charges from the fuel. So the catalyst sends all of the electrons on this side, electron excitement, and then all of the protons that way. You're not actually splitting the atom. I don't know how much to explain here. Let's go this way. It's like a battery with a negative and a positive that you charge when you give it fuel. And the only byproduct is a little bit of heat and some water. The chemistry can get complicated, but the idea is if you have the fuel, you can charge a battery and then that can do work. And you can keep giving it fuel so the fuel cell can keep doing work as long as you've got fuel. Remember, the secret is, do you have to make the fuel using energy, or is this a fuel that you can harvest? So if you can get methane somewhere, that's great. But if you have to use a bunch of energy to make hydrogen, that might not be great. I'm not sure how much you would need for the College Board, so I'm just going to move on. The last thing we have to talk about is solar. And like, I left this for last because there's a bunch of stuff here, but it's been like a 45-minute lecture already. So feel free to pause and stretch and crack some knuckles and go have some coffee. There's a lot to say about solar, but then we're done with this assignment entirely. The good news is there's a lot of sunlight. You really can't control it. Some places get less sunlight. There's probably no way to do solar in Alaska because the winter is very long with very little sunlight. The problem is storage. Like if it only works when there's sun, you get a cloud and you're bummed. You get a storm in the winter and you're bummed. Shorter days, longer nights. Storage is the problem for solar. And you should know that that's a problem basically for all solar designs. But there's like 4 different ways that you can use sunlight. You can design homes passively. You can collect heat. You can use sunlight to make electricity in panels, or you can use sunlight to make heat that makes steam for electricity. So those are the four things you just saw. And I'll explain all those, don't worry. I'm using the term passive, which means there's no moving parts, or active, or something is moving, like you're moving hot water or you're moving electrical current or whatever. Passive solar is no moving parts. It's just a way to design homes. And the idea is they stay warm in the winter because of the design, and they stay cool in the summer because of the design. And you know what's funny? This was all construction for a really long time, and then we got in this period of US history where we made really inefficient homes so that everybody could buy them. And now we're going back to really old school design. Many parts of the world, this is the only type of design because there wasn't a lot of other energy sources, so you had to make your house this way. My grandfather built his house with his own hands. And in my grandfather's house, where my mom and my two aunts were born, that house in the summer, you could have like a really hot day. It's a hot part of Argentina. And in the middle of summer, you go inside and your feet are cold. Like the ground is always chilly because tiles. And then in the winter, when there's like snow outside, you go inside and it's cozy. Like you don't need to wear a sweater. And that's all without using other sources of energy. There's a lot of tricks you can do, like where you put the colors, like dark on the floor to collect winter sunlight, but white on the walls so that it won't heat up a lot in the summer sun. Where you put the eaves and the awnings so that the summer light from above doesn't hit the house, but the winter light at a lower angle goes in to heat up the floors. That's a big deal, and there's easy math for this. In my classroom at the high school, I can show you this because my building was designed using these methods. It's old school, it's a crusty old building. So my eaves in my classroom in room 65 block all sunlight in summer. There's never sunlight hitting the floor. And in winter, there's always sunlight hitting the floor. You can use what's called thermal mass. These are materials that hold their heat or they hold their cold. If you've ever been in an adobe building like the Mission, or you've ever seen how like a stone fireplace stays hot after the fire goes out, so in the morning it's still hot. That's why all fireplaces are stone or brick. Maybe if you've noticed tile floors, how they're like kind of warm after sunset or they're kind of cold in the morning. These are thermal mass, and that's a good idea. Once you heat it up, you want it to stay warm. If it's cool, you want it to stay cold at times. You can use deciduous trees to shade the house. So they have leaves in the summer and you're in the shade. The leaves fall in the winter, so you get heated by the sunlight. Some people use greenhouses or sunrooms to make hot air like in a greenhouse, and then you open that to the home when you need it in the winter. How you pattern the ventilation, or if you let the hot air out, that'll draw cold air in. It's called convection currents. And there's a bunch of ideas. You used to do like a 3-month project where you would build these houses. But because we're all at home now, there doesn't seem to be a way to do this. You should still know these concepts. You may want to watch a quick YouTube that shows you some examples. But I've got a few pictures, like designing the house to use sunlight angles that are different in different seasons, and thermal mass so that you can capture heat or capture cool when you need them. Beneficial currents, where you put the trees, capturing hot air in a greenhouse to heat your home in the winter. Again, the thermal mass. Okay, that was passive. Notice that nothing moves around. You're just using the heat for the house. Nothing moves. That was passive. Everything else is going to be active. So these are pretty simple. They're called solar collectors. You've probably seen them. And this is active now because you push cold water up to the panel. water left in the sun will heat up. Maybe you've noticed a hose on the driveway has hot water when you let it out. And then when the water flows, you're delivering hot water. This is very common to preheat water if you have a fossil fuel heater. Yeah, that's it. That one's easy, I think. Photovoltaics, number 3. Again, I can explain this engineering, but I don't think you need it. Basically, there's layers in a solar panel. So when sunlight hits it, one of them becomes negatively charged and the other panel becomes positively charged. So in sunlight, you have polarity like a battery. There's a negative side and a positive side. So it'll do work. You connect them with a wire and you're going to get electricity when the sun is out. Remember, one side becomes negative, one side becomes positive. So it works like a battery as long as the sun is out. It's charged. These are pretty exciting. And because of global development and solar panels, the prices come way down. In many parts of the world, maybe most of the world, these are not competitive with fossil fuels. But you know, the sun only shines when it feels like it. You can go to places that are pretty sunny. We know where on average this makes sense, but you still have a question of how you're going to store it. Like, what do you do when you need electricity at night, right? So option A is like a sailboat or the Unabomber cabin, the way that the hippies did it, like off the grid. You might have heard off the grid like is a term for hippies that lived in remote places where they were away from society. And the idea goes that you use the solar panel to charge a battery, and then when you need electricity, you let it out of the battery to power your house. And that sounds really good, but you should know that batteries suck. They're really inefficient. Like, average battery in its lifetime is about 20% return. So you put in 100 units of electricity, you get 20 out. That's a waste. That means you need a lot of panels, right? Because the battery doesn't give you back all your electricity. Batteries are super expensive. You got to clean them and stuff. You got to maintain them, check the fluids, so on. Batteries really suck. And by the way, you usually have to have some sort of a backup generator that runs on fossil fuels. So usually this is only reasonable when it's the only option. If you're trying to run like, you know, a speed test in the middle of the desert, well, you're not going to run extension cords, so fine. If you're like living in a cabin way back in the forest and you're trying to hide from the law, okay, it kind of makes sense. On a sailboat in the middle of the ocean, if you have an RV that you take to go in places that don't have electricity, I get it. And there are better batteries on the horizon. But this whole thing with off-grid is not the majority of solar panels. Like 4 or 5 in each class probably have these at home, and you're not using batteries. Most people today have what's called on-grid photovoltaic systems. Here, the panel makes electricity, and you're going to use it right away. Your house takes what you need, and if you're making more than that, that goes into the wires to your neighbor's house. So on a really sunny day, you're running your refrigerator, your neighbor's refrigerator, the other neighbor's refrigerator, and maybe the person after that. Notice that the electricity leaves your house, goes through the wires to other houses. That's a special meter, because then at night, the meter brings electricity to your house. So it's a two-way meter. When it's sunny, you're getting paid. Then when the sun goes down, you're paying them. So you get a credit in the daytime and a charge at night. Summer has more sunlight, longer days, less clouds. So usually in the summer months, they pay you a few bucks at the end of the month. And then in the winter, when the days are shorter and there's more cloudy days, then in the winter, on average, you're buying. So if your parents do this, there's probably 2 or 3 months where they just get paid, and then a couple months where they roughly break even, and then a couple of months where they got to pay back. So this is like a credit and charge, a two-way meter. We say it's stored on the grid because it's like leaving and coming back in terms of credit to your bank account or charge to your bank account. It's stored on the grid. It's not actually stored anywhere. You know what I mean? Like you're storing the dollars using the grid because they pay you, you pay them. It's not really getting stored. There's no batteries. This is a lot of sustainability stuff. No batteries, short distances, so you're not wasting it on wires. Very efficient, very simple, very little maintenance. You just have to blow off the panels a couple times a year. And this is blowing up worldwide. This is becoming really common. For a while there, this looked like an easy way to make money. People were like, dude, I got a big old roof. And so there are people who got into this early on that were planning to make like 20 grand a year, and they just invested in a whole bunch of panels so that they could sell electricity and become a miniature power plant. But the utilities still have to pay for their wires. So they got to charge you somehow. So there's all these unfortunate changes to the economics where it's not as profitable as we thought it would be. You see, they buy from you at wholesale prices. You're selling your electricity like a power plant. You're selling it for 10 cents. And then they're adding the price of the grid, and they're adding the price of the meters, and they're adding the price of the staff, and they're adding the profit. So then when you buy electricity back from them, that's at retail price. You get 10 cents, but you pay $1.50 or whatever the numbers are. So this looked like it would be profitable. Turns out it wasn't profitable. It's still very sustainable. Now, you can be grid connected and be a power plant. So there's mega fields where a lot of utilities are making just like 5 acres of solar panels, and that's just a power plant. They just sell to the utility. And there's the idea of what are called microgrids. That should be underlined. I'm sorry, that's vocab. Microgrid is really common in less developed countries now because sometimes it's cheaper to do this than to build power plants in remote places. You can also do this in communities. Like if you've got a big parking lot at the Walmart, why not shade the cars? And that'll make enough electricity where Walmart can give electricity to all their neighbors instead of paying taxes, for example. So microgrids, increasingly common. And the last thing we have to talk about is solar thermal, or concentrated solar. And the idea is you're going to use a bunch of mirrors to focus sunlight in one place. That makes a lot of heat. So you can heat oil, or you can heat salt, or whatever. This is like when people will burn ants or like etch wood using a magnifying glass, because a whole bunch of sunlight gets focused into one place, and so you're taking all the heat gain and putting it all in one spot. This is kind of cheating the quality question, because you can take low quality heat and make it high quality by adding it to one place. You're just aiming it differently, right? The old school method, which you can see when you fly into Kona in Hawaii, it's like right when the airport, like when your airplane makes the last turn before it lands, if you look off the right wing, it's looking at a big plant like this, where you have parabolic mirrors that focus all the incoming sunlight on that one point. So you run a pipe there, and that heats up oil. Now you're not going to mix oil and water, okay? You're going to have hot pipes with hot oil, and then when you bring cold water against the pipe, that makes steam. This is a really small drawing. I was just exhausted of making the slideshow last night, but I probably should have made this bigger. But if you look over here, you can see that the reflecting sunlight gives you hot oil from cold oil. And then you can take all that hot oil, and when you pour water over the pipes, that makes steam for the turbine's generator. Okay, so This method doesn't make a ton of electricity. Like the economics are just not really great. But what if we could focus a whole lot of sunlight in one place? This is a really, really exciting future for sustainable electricity. These are called solar thermal towers. Um, Another type of concentrated solar, the new school method, and this is a really big whoop. You have a whole field of mirrors which are all shooting sunlight at one spot. So basically you can make as much heat as you want. If you want to raise the temperature, you just add more mirrors and bring more sunlight, right? So the only limit is how hot something can get before it explodes into flame or melts. They could keep adding mirrors. It's just you melt the tower, or you explode your fuel into your medium, you explode it into gas form. So you got to find something that has a really high melting point, like salt, just pure salt. And you can get that stuff up to like 2,000 degrees, 3,000 degrees. Now the point is just like, how hot can we make it before things start to melt? And if you have something at 2,000 degrees, you can store that for like 1 or 2 or 3 days. You can store some of these for a week, and it's still hot enough that that material in a pipe can still make steam. So again, I'm sorry about the drawing being small. Focus all the sunlight, heat up the salt. That salt goes into storage, and you run molten salt through pipes so that cold water coming in makes steam for the turbine. And as that salt starts to cool down, you bring it back through and give it more heat. Now, the secret with this, the reason people are excited, is because you can store the heat. The idea of storage is a really big whoop. That was a really long lecture. I'm going to see if I can upload an hour-long lecture now. And I hope that you got to finish taking notes. I have a feeling this is going to be longer than I expected for you to do all these notes, but trying to be helpful. I hope that worked. We have like one thing to talk about, and then we're done with this whole entire assignment. Okay.